Okay, so now that you've been introduced to the D flip-flop, the T flip-flop, and the JK flip-flop, let's do some more practice with these. Remember, like for the D flip-flop, we added a synchronous or an asynchronous set or reset condition. We can do that with any of the flip-flops. So here you can see three black box models of the circuit. Of a D flip-flop, this is showing with a active low set and reset signal, T also with an active low set and reset signal, and JK with an active low set and reset signal. So let's see how these set and reset signals are going to affect our timing diagrams. Let's first consider them as them being asynchronous, so that way they happen at any time not aligned with the clock edge. Okay, again, we're going to do an example with a rising edge triggered. RET stands for rising edge triggered. D flip-flop with active low, asynchronous preset and clear, or set and clear inputs. Okay, so how does this work? Well, here's our output Q and our inputs S, R. This S naught shows that they're active low. And D and clock and our output Q. So we don't really know what Q is until we get one of these set or clears. So here Q is set asynchronously, so we know at this point that Q is definitely a 1. And we look over set and reset, and neither of these are low at this point, so we just hold the condition until we get to the first rising edge of the clock. This is a D flip-flop, so Q is going to get whatever D is. D is 0, so Q gets 0. Then we move along. Wait for the next rising edge of the clock, which is right here. What is D? D is a 1, so Q gets 1. We move along. Oh, there's an asynchronous reset that happens at this point. When it's asynchronous, we evaluate it even when it's not at the clock edge, so we bring Q down to 0. It stays at 0 until the next edge, where we evaluate what D is. D is a 1, so Q becomes a 1. Moving along to the next edge. At this edge, D is a 0, so Q becomes a 0. At this point, oh, look, reset became a 0 again, but it's already 0, so it doesn't matter. It stays a 0. At this edge, D is a 0, so Q becomes a 0. And then we get an asynchronous set happening. So at that point, the set goes down, the Q is going to go up. So that's a rising edge triggered D flip-flop with active low, asynchronous, preset, and clear signals. Let's look at how this might work for T flip-flop. Here we're going to do an example timing diagram for a rising edge triggered T flip-flop with active low, asynchronous, preset, and clear. Okay, so again we have active low, so anytime we see this drop, we know we're going to set. Anytime we see the R drop, we know we're going to clear. Okay, and remember the T is going to toggle the Q if it's 1. Alright, so here we go. We start off, set becomes active low, so it's going to set Q to 1. Q is set to 1. At the first rising edge of the clock over here, T is a 1, which means we toggle, so Q goes from 1 to 0. We move along, reset goes low, so Q needs to be low. It already is, so that's okay. Now here we have toggle is 0, reset is also 0, so we stay low. Now we have a asynchronous set happening, so at the time the set goes down, at the time the set goes down, the Q needs to go up to be set. We move along to the next edge. T is at 1, which means toggle, so Q needs to change from 1 to 0. Move along to the next edge. T is 0, so we don't toggle, we hold, so Q stays 0. Move along to the next edge. T is a 1, toggle, so we move from 0 to 1. We move along, oh, reset happens, so we reset at this point and go to 0. Move along to the next edge, which is not on the screen, so there you go. There's an example timing diagram for a rising edge triggered T flip-flop with active low, asynchronous, preset, and clear. Alright, so one more. Here we go with the JK. Similar idea. We've got now a JK with the same conditions. Here we go. Reset is low, so Q starts at 0. Go to the first edge. J is 1, K is 0. That's a set condition, so we move it up. Set is a 0 here, so Q needs to be 1. It already is, so it just holds. At the next edge, J is 0, K is 1. When K is 1, K for clear. Remember, we clear. So we clear, and the Q goes to 0. We move along, still noticing that nothing's happening with set and reset up here. We move along. At this edge, J is 1, K is 1, so that means toggle, so we go from 0 to a 1. But then at this point, the reset occurs, so we need to bring it back down to 0. And we move along to the next edge. At this edge, J is 0, K is 1, which is a clear condition, so it's 0, it stays 0. We'll move along to this next edge. J is a 1, K is a 0, and that's a set condition, so we move it up to a 1, move Q up to a 1. Then we have an asynchronous reset happening, and so we pull it down to 0. So it's important as you're going through these timing diagrams to always evaluate what's going on with the asynchronous signals. So as you're moving along, be sure you're keeping track of what's happening to these because they take precedence over the clock edge. And then always evaluate J and K at the clock edge to see what Q does. And let's look at one more example. We're going to look at here, we're going to write the VHDL code that describes a T flip-flop shown on the right. Use a behavioral model in your description. Consider the S input to be active low, asynchronous input that sets the T flip-flop outputs when asserted. Okay, so we're just going to look again at a VHDL model to model this circuit. And again, S is an active low, asynchronous, which means it's not going to go inside the rising edge of clock statement in the code. Okay, so here we go. We have our entity description, which has T, S, and clock as our inputs, and our output is Q. In our architecture, we're going to create a temporary signal, T-temp, and you'll see why in a moment. So our signal T-temp is of type standard logic. We're going to start our behavioral model with the process statements with the T, S, and clock in our sensitivity list because we want this to be evaluated anytime these change. Okay, so we have an asynchronous active low set input. So the first thing we start off is with the asynchronous set input. So if S is equal to 0, active low, then Q is going to be set. Q will get 1. Else if, now we can use our clock condition. So else if it's the rising edge of the clock, then we're going to set our temporary signal T-temp to T, which is our input, exclusive OR with T-temp. So this is why we needed to create the temporary signal, because we need T-temp to hold its previous value and the current value. And you can't do that when you specify T as an input, because then T can only be an input, but signals can be both inputs and outputs. Okay, and then we have no else at the end, which implies else just hold whatever you have. So we have our asynchronous active low set input, followed by our characteristic equation for the T flip-flop. Remember when we discussed T flip-flops, they were T exclusive or Q. So we do that by using a T-temp variable to hold what Q is. And then as you can see here, we assign Q to T-temp. And this, once again, the signal allows us to have it be both an input and an output at the same time. So this is how you model a T flip-flop in VHDL with an active low asynchronous set.